So this is about a sliding mode control. Okay, so I try to switch to the one of the control strategies as a SMC. So for a sliding mode control, today I would like to give you some introduction to SMC, some design and also applications. But of course, we have another session about SMC. I will discuss more, maybe also another lecture. But today, so let's start with the SMC. So about the introduction to a sliding mode control, basic concept, a type of variable, a structure control. So and some other issues about the type of system and design. So first of all, this is my recent book. So you see that the book is published end of 1st of May. So if you are interested, I can provide you more material from the book. So the book is about a sliding mode control of fractional order system. I'm not sure if you are working on the FOS fractional or not. But if you are interested to this kind of the systems, so you can contact me. And if you are interested to the book, because the book is published now is not released, but in 1 month I have access to all the book's content. But if you are interested, feel free to contact me. Okay, so now you see that the sliding mode control, it becomes a very important topic because of this robustness, and that's it. And also to look at the response in the efficiently in terms of the managing the response in the finite time. The finite time, robustness, these are some issues we are interested to use it for some complex system, and that's it. We try to discuss about SMC also for the CPS, and then to see that how we can get some enhancement. So the origin of the feedback control, we discussed about the control from ancient side coming to the classical control, coming to the advanced control. It means that the control is developing and developing very fast. And nowadays, based on the topic of the course, you see that now the resilience control becomes a hot topic in the CPS. And that's it. We need to a little bit look at some new trends. Okay, so of course, from the state of the art, of course, maybe you are familiar that so the relay is one electrically operated switch. It means about switch control. Okay, so how to switch from the state 1 to state 2? This is kind of the switching or the jumping. So the relays also would be one physical basic device. So or it was useful in some circuit design, and therefore the relays was introduced or was integrated to the control system to perform some logical operation. And that's it. This kind of the variation in the structure by changing the modes of the system from 1 to 2, so or the vice versa. And this is the on-off control actions. So they bring some difficulty in control, because if you do any kind of the switch, then you are jumping, and then there is some nonlinearity in the system response, and that's it. One of the problem appeared from the relay-based control is about the nonlinearity is appeared in the model because of the switch is appeared in the system model. Okay, so but of course there is a lot of development from late 50s, 60s, and also very famous person. He contributed a lot basically to this topic is basically the Professor Etkin basically in his 1964. So he tried to introduce the variable structure control is a VSC. Okay, so he introduced the VSC, variable structure control, and then later on is changed to SMC as a sliding mode control. But what he proposed, he also focused on the theory of the relay-based control, and based on this kind of the theory, and then he need to look at some variation in the system, and that's it, the VSC, or to come into the SMC. So these are the some keywords. So basically has been introduced. So originated from the work done by the Professor Etkin. Okay, so the basic concept in a sliding mode control. So the first of all, the basic terms, it says that we have some dynamical system like this. Okay, so here we can see that for this equation, we have a control signal U, and we have a system state X. And then here you need to introduce some logic, and this logic is introducing by the function sigma x. Okay, so this function sigma x, or we call it a switching surface or a sliding surface. So is a sliding variable. So now the sigma xt is a sliding variable, and sigma xt is 0 is a sliding manifold. So what does it mean, a variable, and what does it mean, a manifold? So the sigma x zeros is try to give you one surface in the 2-dimension or even one line, but all the variables should approach to this manifold, and that's it. A sliding manifold can be introduced and should be selected, should be chosen, but this depends how many states you want to control. And that's it, you need to add some dimension basically to the sigma x. So now the sigma x, depending to the control signal dimension m, it means that you want to control, for example, n variables, and therefore you can define the sigma xt based on this as a sliding variable with this dimension, vector dimension, and then you try to basically to design the control. So the concept of a sliding mode, so as I showed you before that, so it means that all the state trajectories, basically, so that based on this difference n minus m, it means that this sliding manifold is a subspace of the system state space having a dimension n minus 1. So it can be a sliding surface or be given by the intersection of the several surfaces. So this could be one single surface, or this could be either as an intersection of the several surfaces, and that's it. So this could be your sigma zeros, or this could be your sigma zeros, okay? So assume that for this kind of the sigma zeros, and then all the state trajectories, so they should converge basically to these sections. Okay, so now if the state trajectories continuously cross a sliding manifold, since it's in its vicinity of this state motion, always directed toward the manifold. So now the point is that when the state trajectories is hitting, so for example, this sliding manifold, and then they can push forward to move to the sigma zeros, and this means that the convergence can be guaranteed if we follow this concept of the sliding mode. Okay, so if you look at the design ingredients, so there are two elements. One is a sliding manifold. The second is the control law. It means that a sliding manifold is a sigma x. It means that how to choose the sigma zeros. And in this case, so this is one parameter to be designed. So the system in a sliding mode, basically we try to look at how to asymptotical state can regulate it to zeros if they are basically coming to the sliding manifold. But the control law, it has to be chosen in order to enforce. This is very important. A sliding mode. It means that after a state is hitting, for example, or approaching to this sliding manifold, there should be some motion around of the surface. So it means that there are some sliding motion. And this means that the control law should be responsible to guide, first to guide a state trajectory to this sliding manifold, and then to be remain after some saturation or some fluctuation around of this sliding surface. So a sliding mode needs to be enforced in a finite time. Okay, so reaching from this initial condition x0 to this point, so this should be done in a finite time, and that's it. The one of the characteristic of the requirement for a sliding mode control or a sliding mode motion is the finite time behavior. This should be done. But please pay attention that in control we have a two topic, finite time or the fixed time. Okay, so these are the two keywords. So basically the time to time, so the fixed time. So you can see many state of the art. So a sliding mode can be done in the finite time, but what does it mean the fixed time? Fixed time, so it could be also one representative of the finite time, but the fixed time, it means that this should be designed by the user, for example, at the one specific time, so that the control should reach to the target. But this is different from the finite time, and that's it. If you want to design the fixed time control, so you need to pay attention that the time is already given, but the finite time is a short time. It means that the TF so should be less than infinity. Okay, but as long as this TF become less and less, the system become quicker and quicker. But the finite time is different from the fixed time, because in the fixed time you already have a one force, one requirement to reach in this specific time, and that's it. A sliding mode just presenting the finite time. But if you want to bring it to the fixed time, so we need to look at how to modify the control strategy to satisfy this point. But this is another research topic. Just I tell you that another keyword might be you are interested to see what is the difference between the finite time and the fixed time. But SMC is only can prove the finite time, but SMC cannot guarantee the fixed time. But if you want to reach the fixed time, you need to modify your design, and that's it. These are the important topics. Okay. So the equivalent system and its properties. So the system in a sliding mode, it has the two interesting properties. One, order reduction. This is very important because when you design the sliding mode control, the system sliding mode changes the order from n to n minus n. Why? Because you already m is coming from the dimension from the sigma x zeros, okay? Because when you add some algebraic relation from the dimension, because sigma x, it belongs to Rn, okay? So now you can see that by designing this sliding surface or with the dimension m, you try to reduce the system order so to the n minus n. And this means that the computation also can be enhanced. So the invariance property is insensitive to the match uncertainties. It means that the uncertain terms affecting the system on the control channels. So that's it. This is one of the properties insensitive to this kind of the matching uncertainties, and this is also about the robustness. So the reduced order state equation describing the system in a sliding mode is called equivalent system. So basically this reduced order after designing the sliding surface, when you got the reduction in the order to n minus n, so this reduced order, we call it the equivalent system. So this kind its dynamics can be assigned by suitable design a sliding manifold. So now important is this, how to design this sliding manifold sigma x, because all the challenge is related to sigma x. So one example, so we have this unstable second order system. So if you look at this system, you will see that this system is unstable. And then for this unstable system, we want to design the control input as a u minus 3x1 or u equal 2x1, okay? So if you do like this, if you choose the control signal u as a 2x1 or minus a 3x1, so then you see that the control system has an unstable focus if the u is minus 3x1 and a saddle point if the u is 2x1, okay? So if you look at the control signal u minus 3x1, and if you look at this equilibrium point, you see that they are diverging. They are diverging to infinite, okay? And this means that you have this unstable focus. This is the unstable focus for u minus 3x1. And then for this, for the case of the u equal 2x1, then you have such a saddle position. You see that if you look at the state trajectories x1, x2, with the control signal u equal 2x1, you see that a state trajectory, they have such a behavior. So this behavior is the saddle point, and this behavior is unstable focus. And this is a two behavior you can see for the two different control. Okay, so now you are choosing another manifold. If we choose a sliding manifold sigma as a C1x1 plus C2 equals zeros, and C1 is positive, okay? So in this case, so the design control input as a combination of the two previous control laws. Okay, so now we are choosing the control signal like this. U is the K sigma x1, x1, but the K sigma x1 is minus 3 or equal to if the sigma x1 is a positive or if the sigma x1 is negative. So you remember that in previous slide, minus 3 was the u minus 3x1, right? And also this was the u1 and this was the u2 is a 2x1, okay? So we notice that this unstable system, this is a very good example. This unstable system with the two different control signal u1, u2, again is unstable. But if you bring it to the context of the sliding manifold, a sliding mode, but you choose such a switch because you are switching if the sigma x1 is positive or sigma x1 is negative, it's become minus 3 or 2. If you give a switch between the two control, and then you can see that this is a u2 and this is a u1, okay? Then you can see that the control signal, it brings you some advantage. The control law is a variable structure control law. It means that the control, there is some variation in the structure. The control system becomes the VSS, variable structure system, VSS. And this means that let's see what is the benefits. So based on this benefit, the combination of the two control laws ensures the conversion of the system state to origin. This is very important. So as long as you are using this control signal as we discussed here, u is the kx1. So based on this control signal, if the sigma x1 is positive or sigma x1 is negative, then you can see that these can converge. So basically to the sliding surface, because here you are choosing the, you should choose the sigma like this. Okay, sigma is this formulation. So here you have a sigma is equal C1 x1 plus x2. Okay, so for this switching surface, so if you see that if the C1 is bigger than 1 or the C1 is less than 1, then here you have such a basically the 2 sigma is a sigma x2 plus C1 x1. So in this case, all the state trajectories, so basically can converge basically this sliding surface. So from any initial point, so from this area or from this area, so basically the system can convert to this sliding manifold. So in this case, if the C1 is less than 1, a sliding mode is enforced. It means that we need to see that for the case of the C1 is less than 1, so then in this case, so we can reach basically to the sliding manifold, and this basically system can be stabilized. But for the sigma, for the C1 bigger than 1, there is no convergence. You see that this is a dashed line, okay? So in this case, what we can notice that the parameter C1 should be less than 1, and then all the state trajectories can be approached to this manifold. Okay, so another example is we have the double integrator. So this is another example. So it means that for this example, if with this constraint over the control signal u is less than 1, so you can choose the a sliding manifold, the sigma like this, okay? Usually you can choose the linear shape for the sigma, like a C1 x1 plus x2 equals zeros, and the C1 is positive. So if sigma is equals zeros in a finite time, is a TR, the finite time as a reaching time, and sigma zeros, so a sliding mode, then the dynamics of the equivalent system in a sliding mode is of read disorder like this. Okay, so now this system says that if the sigma is equal to 0, then the system has a reaching time as a finite time TR to the manifold sigma zeros. And then when it reaches to this manifold sigma zeros, so after t bigger than TR, the system has a sliding motion, a sliding mode. A sliding mode, it means that, for example, if this is your, for example, this is your sigma zeros, for example. So when the state trajectories is from the x at the time zeros. So when this arrives at this surface, and then it start to have some motion like this. So this time, so from here to here, it goes at the time TR, and after the TR, here after TR, there is some oscillation, and this oscillation we call it a chattering or a sliding motion or a sliding mode. Okay, so for this dynamics, you can see that because the sigma is this, so if you want to write down so basically the equivalent system, because equivalent system, you need to add the sigma 0 to this state. So then you can see that the x dot 1 plus C1 x1 becomes zeros. Why? Because you can see that from this equation, you have x dot 1 is equal x2, okay? X dot 1 is equal x2. So from here, x2 is minus, from here, x2 is equal minus C1 x1. And then if you bring it here, so this becomes is equal minus C1 x1, okay? And then if you bring this to the left, you can exactly get this equation. So this equation, you can obtain it. But what does it mean, this equation? This equation means that it is equivalent system. And if you look at the state x1, you can get this formulation, okay? So this formulation says that because of this exponential at the time TR, so the system can reach to the surface, and then the system can, there is a guarantee that the state can be vanished to zeros. But the point is that you need to choose C1, because by changing C1, the performance is totally changing. So now for this system, because for this double integrator, assume that you design the control input. So the control input is for sigma positive is -1, for sigma negative is 1. Of course, there is a discontinuity at the sigma zeros. Okay, so for this system, if you want to apply in the simulating, so you can choose like this. So like this saturation part. And then for this switch model, you can put in the simulating, and then you can basically to design the control. Okay, so if you start to close to look at the simulate of this closed loop scheme, so based on this kind of this saturation part, so we can see that the result can be obtained. So here for the small C1, if the C1 is a small, and this is for the large C1. So if the C1 is a small, the state trajectory is following the parabola arc, and then and reach the line sigma zeros, because this is a sigma zeros, and then basically they can reach. And then a sliding, they have a sliding toward the origin as a sliding mode. Then they can reach to the surface. So at any time that they can reach to the surface, and then to have some sliding motion to the surface. Of course, before they are following some parabola arc. There's a parabola arc. They are following such a shape, for example, something like this, and then they go to the origin. But if the C1 is large, for the case of the largest C1, so you can see the state trajectory follows sequence of the parabola arc closer and closer to the origin. So this is quite interesting that they follow different parabola. You see something like this, and then finally they can come closer to the origin, but no sliding mode is generated. So this means that if the C1 become bigger, you don't see any sliding motion, sliding or the chattering. They can become on the different parabola arc, and they are become closer to the origin, and then they can converge to origin. So this is another behavior of the system. Okay, so now you can perturb the double integrator with an uncertain bounded term. So let's assume that in this, because was your this double integrator, right? And this was your control. Now let's add this term. So now we want to add this additional term like this. We want to add the function dx1, x2, and t. And you remember that the sliding surface was this. Sigma is a C1 x1 plus x2. So this term is the uncertain bounded term. And if you add it, so here we can say that if sigma is zeros in a finite time tr, reaching time, and sigma zeros is we have it for bigger than the time bigger than tr, we have a sliding mode. And the dynamics of the equivalent system in a sliding mode is this. So you see that these dynamics can be obtained. So from this mathematical model. So the uncertainty doesn't affect the system in a sliding mode. So this is very interesting. So maybe I think this could be a good exercise. So you see that even if you add such a disturbance, such a uncertain bounded term, so it never appeared in your equivalent system, because equivalent system is the same as before. So it's very interesting that you can see that x.1 is equal to x2. And as I showed you before, x2 is minus c1 x1. And you can get this. So what does it mean? It means that this function d is it doesn't affect the system in a sliding mode, because of a structure of these dynamics. Okay, so what we can learn. One is about the VSS, about the variable structural control VSC and VSS. So making the system become the variable structural system can have a stabilizing effect. So it means that this switch in the system, such a variation in the structure, so then you can stabilize the system. A sliding mode enforcement depends on the choice of the control law. So it means that it's very important to this a sliding mode enforcement depends on the choice of the control law. It means how to choose a sigma X. And the system in a sliding mode is of a radius order. It means that when you design the system as equivalent system is a radius order, it means that the computation is decreased. The system dynamics in a sliding mode can be arbitrarily assigned. It means that you can choose the system dynamic in a sliding mode, depends on you, but we need to pay attention that how to select this a sliding manifold, and this is the important task. The system in a sliding mode has a nice robustness problem. So the system is robust. And this is one of the advantage basically we have from a sliding mode control. Okay, there are different type of the variable structure control laws. It means that one of the variations is that so as a relay control. So this is one variable as a structure VSC. So the relay control or the relay, so the control signal UIT depends on the sigma I, positive or the negative. So they should have a two levels control, UI plus, UI minus. So this is it with a dimension M. And then you have a sliding manifold sigma IX equals zeros. In total, you can find this a sliding manifold sigma X. Okay, so the design phase consists in designing the sliding variable sigma X and the smooth function UI plus and UI1. It means that all the design, so whatever should be designed, we need to select the sigma X, and also we need to select this smooth function. So these are some design function or design variables. So you can choose it for the relay control. So a state feedback control with the switching gains. Okay, so now you have a control signal as a state feedback. U is a psi x multiplied xt. So this is a function psi. So it's a matrix. You can see is the matrix n by n. And each term of this matrix is phi ij can be selected from this mathematics. It means that it depends on the sign of this function. So positive or negative, you have two levels, alpha ij and beta ij. So in this case, if you, for instance, the unit vector control, so if you choose the control signal u like this, so this is you know that this is equal to k multiply the sign is sigma x. So this control signal is also the unit vector. They call the unit vector control. So it also looks like this. You see that you can, for example, choose it like this, and this means that the unit vector control is one example for the state feedback control with switching gains. But this is a general shape, and this could be another control, but you can choose like this. So the philosophy behind of the unit vector control is taken from the state feedback control with the switching gains. Okay, so there is some other control strategies, control based on the simplex of vectors. So that's it. This was one unit vector control, but you can think about the simplex of the vectors. In the multi-input case, the variable structure control philosophy can also be implemented by designing a set of n+1 control vectors forming a simplex in Rn. So the control system switches from one to another after this. So now you see that the idea behind of the simplex of the vectors is to give more flexibility by designing the more control vectors. With that, you need to design a set of n+1 control vectors, and then the system can switch from one to another one. So now you have a more switch possibility. So if you look at this publication as a most input, a sliding mode control of the class of the answering nonlinear system, you see that so you can get a better idea that how this simplex of vectors so can be realized. Okay, so there is some other discussion about the type of the system. So basically, the one is the canonical form. So in the canonical form, the assumption is that the system is nonlinear with respect to the state variables and linear with respect to the control variables. Okay, so it means the system should be affine in the control input. So it means that something like this. So this is a basic, we call it the system is affine in control input, nonlinear respect to state variables, and also the linear respect to the control input. So this means that this assumption means basically I'm talking about this dynamics. The proof of the existence of a sliding mode and the design of the variable structure controller are simplified if the considered nonlinear system is expressed in one of the following canonical form. So if the system can be represented in the canonical form, it means in the reduced form. It means a state vector xt can be split into the two vectors x1, x2. Okay, so if you could represent it like this, x dot 1 is a1 xt, no control, and x dot 2 has such a affine shape respect to the control. So this model is a reduced form, and that's it. If you have such a model, it can be proved that the proof of the existence of a sliding mode is possible. We can prove it, and also we can design a sliding mode control. So this means that if you have any model system like this, the task is can be guaranteed that you can obtain, you can stabilize it, and also you can find the control. So there is a contractibility form. So this is a reduced form, another is a contractibility form. The system is split into the M subsystems. Okay, so the M is the number of the control input. Okay, so each of them is the Bronowski canonical form. So let's assume like this. This is a contractibility form. Assume that a state, it has a dimension M. So we basically, and each of the xi has a dimension ni, and the whole system has a dimension n. So now you see that the system should be split to the M subsystem. So now you have an M subsystem, and each subsystem has a dimension ni. So the final system is x dot equal ax plus fx plus bxu. And the A is a diagonal AI. And now you have for each subsystem x dot I, you have this mathematical model with this matrix AI, this AI, this is a Fi, this is a Fi, and this is a function Bi. Okay, so if you could represent your system dynamics in such a shape, so this is a contractibility form, and contractibility form consists of the M subsystem, and is the number of the control input. Okay, so again, for if you represent like this, again, you can guarantee stability, then you can also obtain a sliding manifold. So another is a decoupled input output form, but this is for the size. So in the single input, single output case, assume that you have a nonlinear system with the output y as a cxu. This is your measured data for the size system. The system relative degree is the order of the time derivative of the y in which the control U first explicitly appears. So if you have the MIMO case, it means the y belongs to the Rm. So if you for the given output yi, the associated relative degree Ri is the order of the time derivative of the yi in which at least one of the control variables ui first explicitly appears. The system relative degree is this. It means that this is the relative degrees for the m for the m input, because the order of the y, the output is m. So then you have a several R1 to Rn, and each associated relative degree Ri is the order of the time derivative of the yi, in which at least in one control variable ui is explicitly appear. Okay, so but maybe if you are, I forgot to introduce the relative degree, but relative degree, the definition is this. But if you work with a nonlinear system, so I think it means that you need to get the derivative from the yi in order to get the control ui out of this. So, but if you need more information, I can send you another textbook so to read more about this. But if you search on the internet, easily you can see that what is a time derivative. So time derivative means you need to take one or two or three to four times the derivative of the variable yi in order that the ui should be appeared explicitly, and this means that this is a relatively decrease. But the system relatively quickly. So for the whole system is R is equal R1 to Rn. If R is equal N, if the total relative degrees of the system is equal N, the system, this can be represented as a set of the decoupled differential equation like this. Now you can see that for this relative degree Ri, you can see for this derivative, ui is appeared here. Okay, so now the question is that if you represent the system like this for this MIMO case or the size case, the system is represented in the decoupled input-output form, and then for this case again, you can design the sliding the mode, and you can find a sliding surface, and you can stabilize it. So this is a canonical form. Okay, so the another form is the normal form, but I think because of time, if you agree, I think we can stop at this form. And next time when I want to continue the topic of the sliding mode, so then I can basically continue this part and then to discuss. Because of the time, I think we can stop at this slide, and the rest we can discuss it next time. Do you have any question?
Yeah.
Or?
Thank you, sir. Yeah, we can take one or two questions from the participants.
Yes. Okay, so I can provide you all this material present today to give it to the Dr. Dipayan, and then you can get access the material. But if you have
Yeah.
any question, so you can come to the next session, and or you can send me an email, or we can discuss it in the next meeting, so to discuss about it.
Surely, sir. Surely, sir. I will share with them the PPT, and I request the participants to please go through the PPT. And meanwhile, if you find any queries, uh, you keep those queries in the next sessions. Thank you, sir.
Okay, thank you very
Yeah,
much. I think
yeah,
for today, but we can meet continue the lecture in the next session tomorrow, basically.
yes, sir. Yes, sir.
Okay,
Tomorrow, the conversation will start from 14 hours IST only.
okay. Thank you. Then keep in
Thank you,
touch,
sir.
and then thank you. Then have a nice evening. So then see you too. Thank you. Bye bye. Thank you.
Thank you, sir. Thank you. Thank you. Oh, okay, participants, then we can conclude the day one sessions over here. As I requested to all of you, please go through the materials that I will share after receiving from sir. And you take a note of your queries, and you can ask your queries in the next meeting. So with this, we are concluding day 1 sessions over here. The next session will start tomorrow as per the schedule. So thanks.
Thank you, sir.
Yeah, thanks to one and all for having your patience and uh, attending these sessions throughout. So you guys